right? Our studio.
You're talking about that. I'm like,
So start this. I asked you to create those subsets, right? How'd it go?
it's working, but it's not subsetting correctly.
Okay. It's not subsetting. Which one?
So like the first one that you did last class, I guess what gives me 4 sites.
Okay. So this one. Right? So the levels tells us what levels we need. Right? So we've got A, B, C, and D. That says what we need to use in our subset function. All right, Oaks, A double equals A, and site or site double equals C gives it, pulls out sites A and C, right? Then the aggregate function should give us 2. Did you use this Oaks? Oh, because you used a single equal sign for the first set. So we need our double equal sign because the double tells us that it is a logical statement. 1 equal sign says save site as A. So now we have 2, and you have the same values up here, 24.66. All right, so I'm going to create my subsets, and I'm going to do it rather quickly. So we have a total of 6. So we have AB, AC, AD, BC, BD, and then C and D. So just every pairwise combination. So I have 6. So I'm just going to do, I copied that first one because I knew it worked. All right, I knew it worked. And then I'm just going to paste it. And I'm going to do all 6. And then I'm just going to update them. So A, B, A, C, A, and D. Then we've got B, C, and B, D. And then we got C, D there. So that's change of our name. And then I'm just going to change which ones we are fixing. B, C, and B, D, and site D. Now we have all of our sites.
Did we do CB too? Yeah.
Yep. All right. Got all of our sites. So we're caught up. All right. So just housekeeping stuff. We've got. I'll get the exams back on Monday next week. Should get them back on Monday. If you don't get them back, the grades will be posted, so you can look at it. Our final is on Wednesday of finals week. That'll be our closed book portion. That is also the day when the take-home part will be due. I will probably make the take-home go live on like Friday before. That way you have the weekend, you can work on it. The take-home is the application part, that's what it is. So you're gonna demonstrate that you can actually do this stuff in R and can interpret stuff in R. It will be a little bit longer because it is take-home, all right? But for the most part, it's going to be the same type of format. Here, do this test, do that test, use QQ plots to answer this question, and so forth. Second thing is, you mentioned it, you jogged my mind, the IDEA evaluations. All right, you're going to get hit with emails for it, right? About to take it and everything, and so. Then I will post it and put it up here. So the IDEA evaluations, I do give extra credit based on our response rate. Because you need a higher response rate. Let me get this up here, and then we'll put it up. Here we go. Restricted submitted. So this is posted on Blackboard. It's the announcement. You'll probably get an email. Response rates start at 50%. So as soon as we get half the class, we'll add 0.5%. For every 10%, we'll add another 0.5%. So if we get 100% response rate, you get 3 percentage points added. This is to the final course grade. Right, so this isn't to like the final exam. This is to the overall course grade. So it could be significant, especially if you're like on the cusp of a letter grade. So we can look at it. We'll look at it next week, see what the response rate is, and go from there. All right? All right. We've got our subsets. Why are we doing subsets, by the way? Step back. Why are we doing the subsets?
The pairwise test only works with 2 groups.
Pairwise tests only work with 2 groups. Why are we doing pairwise tests? Variances aren't equal, right? And we ran Welch's ANOVA. What was the result of Welch's ANOVA? I just what did you say? I missed it because I did this in the wrong spot. Created the six subsets.
Means are different.
Yeah. Okay. So yeah, means are different. So we're doing the pairwise test to figure out which means are different. And I'm going to go up here. So what if we want to pull out our, we saw 2 levels. What if we wanted to pull out B, C, and D? We could just add on to our logical. And that's as simple. So just for kind of completeness, I'm going to add this on here. But we don't usually pull out 3 groups. All right. So this is why we're doing it. So we have our subsets. And I do note the other option for the logical expression is using the and sign, which means and. But we never use this for subsetting. The question is why? Why don't we do, if we were pulling out sites A and B, why don't we do site is equal to A and site is equal to B? Let's fix this. For example, why don't we use and like that? Why don't we do that? Why don't we do that? Why do you think it wouldn't run? It won't run. I mean, it will. I mean, R will run it. But why?
pull them together and not keep them as two separate groups?
Oh, is it like an and or kind of deal?
Well, yeah, so we used or,
Okay.
right? So he said we pulled our individual and it could be in site B or site C or site D. Here it says we're going to pull the individual if they're in site A and they're in site B.
Nothing in both of them.
Yeah, the groups within site are mutually exclusive. What does that mean? Individual cannot be in two sites at once. Simple as that. So will it run? Yes, it will. What will it give you? An empty vector. So the and has, if we were doing two different variables, so in grad stats, we're going to subset based on two different variables. So we had, let's say we had site and we had age. We could pull out all individuals of a specific age from a specific site. So now we could specify age is equal to this, site is equal to that, and that pulls out our appropriate combination. But we can't use and when we have a variable where the groups are mutually exclusive. So, all right, so we're getting ready to run our pairwise t-test. We violated equal variance. So we can't run a regular t-test, which is basically the premise of a 2B's HSD. But we can run a Welch's t-test. So Welch's t-test will adjust our variances. We'll adjust our p-values for this unequal variance. So our question for Welch's t-test is, are the means equal? All right. We're going to use it with one categorical variable, that's our independent variable, and it has to have exactly two levels. Can't run it with more than two. We have a measurement variable, that's our dependent variable. Our null hypothesis is that the means of our two groups are equal. The alternate is that the means are different. We can also specify directions if we wanted to. So this is our two-tailed test. All right, so that's part of our two-tailed test. If we wanted a one-tailed test, we would say a group mean is larger than another, or vice versa. All right, the assumptions of this test is that data are random and independent, and data are normally distributed within each group. Are these the same assumptions as a regular two-sample t-test? Yeah? Are we missing any assumption? Data are homosedastic. The variances are equal. We don't have that because Welch's t-test will fix that. All right, so if we were trying to run a t-test, a two-sample t-test, and we violated equal variance, we could run a Welch's test to answer our question. All right, so Welch's t-test adjusts for our unequal variance, just like the Welch's ANOVA. The power of the test is nearly equivalent to a standard t-test, which is why some people recommend always running a Welch's t-test. But many view this test to be a little bit more conservative. That's why it's not quite as powerful, which makes it a little bit more conservative. So it's harder to reject our null hypothesis. But they say, who cares? Because the chance that we have exactly equal variance is pretty slim. So even with that slight variation, people would say, let's just go ahead and run Welch's t-test. Our test statistic is a t. Fix that, I had F. Our test statistic is a t, it's a t-test. Our degrees of freedom gets reported. This should be a decimal point. It should be a decimal number. And then our reporting, we're going to use conclusion, or write our conclusion or interpretation, our test statistic, degrees of freedom, and our p-value. And for the degrees of freedom, 2 decimal places. Basically report what R gives you. This one's pretty easy. We already know the function, it's t.test. We're going to write it as a formula, but now we're going to say var.equal equals f, because we're going to say variances are not equal, and that's the change. So, as an example, here's the example using sites A and B. So we are comparing diameter as a function of site. The data that we're going to use isn't the full data. It's not the full Oaks data set. It is our subsetted data set that only has A and B group in it, or A and B sites. And then var dot equal equals F, and I get this output. Now, I say we do not interpret this output yet. Why not?
You have to interpret them all together.
Yeah, we're going to interpret them all together. Why? Okay, because we're going to determine where the difference is, but why do we have to wait until we have all of our p-values? That was on the bottom. So we don't interpret this test. Why? This p-value has an alpha equals 0.05. All right, so this alpha, or this test, has an alpha, we have a 5% chance of falsely rejecting our null hypothesis. But that's just for one test. But this isn't, but that's not exactly what we want. So this p-value isn't exactly correct because we are going to make a total of 6 comparisons. Therefore, our overall alpha will be larger than 0.05. We can fix this by adjusting our p-values. But we do that after we run all remaining tests. All right, we're going to do that after we run all of our remaining tests. So at this point, yeah, p-value looks like it's going to be different. I look at this and say, yes, groups A and B are different. Why can I say that? Because I know that our adjustment won't be enough to raise a p-value above 0.05. But I know that because we've been lecturing on this for numerous years. All right. But also, it's based on the number of comparisons that we're running. All right. So what I want you to do, we're going to run the remaining pairwise tests, and we're going to save each of the p-values. All right. Why are we going to save each of the p-values? Because we need those p-values to know how big of an adjustment we need to make. All right, so it's not necessarily the value of the p-values. We need to know the total count. So in this spot, I'm going to start it with our first p-value. I'm going to create a vector called p-val for my p-values, and I'm creating it as a vector. And with each test that I run, I'm going to save this p-value. All right? So I say here, run the remaining pairwise tests. So what I want you to do is, we already ran A versus B. I want you to run the Welch's t-test on the remaining 5 combinations. And every time you get a p-value, you add it to our vector. So our vector of p-values should have a total of 6 p-values inside of it. All right? And again, at this point, I think copying and pasting might be the easiest way to do it. I'm going to move this off screen so you can work on it, and I will work on it and get my p-value. How's it going? Did you get them? I took that first t-test, copied it, pasted it 5 different times, and just changed our data set. Just incremented it. So copying and pasting saved a little bit of time. Then I ran them, and what I did was copy each of the p-values, pasted it down in my vector. So I kept kind of going up, copying, pasting, copy, paste, until I get my vector, my p-value vector, and I have 6 values in it, 6 different p-values, each one corresponding to a different pairwise test. And I was very methodical just to make sure that I hit all 6 combinations. Is everyone here at this spot? All right. So we need to adjust our p-value. Why? Because we need a family-wise type 1 error rate of 0.05. The test, each of these tests has a 5% error rate, but we're doing multiple tests on the same data set. And that means every time we run the test, our error rate's slowly increasing. It's making it more and more likely that we falsely reject a null hypothesis, or in this case, that we falsely conclude that group means are different. All right, so what we're going to have to do is take our p-values and adjust it for the number of combinations, or for the number of tests that we actually run. All right, so we're going to have 2 options. And the adjustment's actually real easy, because there's a p.adjust function for us. We got 2 options that we can use. We can use Bonferroni adjustment, or we can use Holm adjustment. And there's more adjustment options. All right, so if you're in like clinical studies, you may choose to do, let's say, Hochberg's, or maybe another type of adjustment method. But these 2 are probably the most common. Bonferroni, more so. This is the most common, it's easy, it's acceptable. You can actually do the Bonferroni adjustment by hand. There's an easy calculation where you basically take your 0.05 and you divide it by how many combinations, and that gives you your new threshold, your new cutoff to say, instead of rejecting at 0.05, we're going to reject at 0.025, or we're going to reject at 0.01, all right? And that's kind of why Bonferroni is so common. You could have done it by hand. Also, SPSS has a Bonferroni checkbox, and it's just acceptable. But it's a bit more conservative. It's a bit more conservative, so it'll be harder to reject the differences or to find differences than Holm. So Holm I like because it's a little bit more powerful, which means it's going to be a little less conservative. All right, this is gaining acceptance. I have seen it, but your choice between Holm and Bonferroni, that's your choice, all right? If your advisor says you need to use Bonferroni, use Bonferroni. If your advisor says, nah, go with Holm, use Holm. Either one is going to work, all right? So what we're going to do is use the p.adjust method, or p.adjust function. And then we're going to specify our method, all right? So the p-values that we give it is a vector of p-values. That's what we've created. What R will do is count up how many of these p-values we have, and then make the appropriate adjustment. Method will be written as method equals Bonf or method equals Holm. Now, we could spell it out, Bonferroni, but can you really remember how to spell Bonferroni, that it's 2 R's and not 2 N's? I can't remember that. I can't keep track of it. So what R will do is look at abbreviations. You can't use just H for Holm, because there's also H for Hochberg. You can't use HO. So I think home's easy enough to just say home, but bond is going to work. So for us, we do p.adjust, p-val, that's our vector, and then method equals bonf, or we could use method equals home. Either one is going to work. And what we're going to do is look at both of these. Oops. Make sure you run your p-val, make that vector. And you're going to see we get two different values. All right. So each of these are the comparisons. So I'm going to do. We've got AB is first. Then we have AC. Then AD, BC, BD, and CD. That's the order that I did it in. So this is the A and B comparison. This is the A versus C, A versus D, B versus C, B versus D, and C versus D. All right, so that's the order in which they get reported because that's how I entered my p-values. How they adjusted it is slightly different, but they normally don't change our conclusions. All right, so normally what you ultimately determine from one is probably going to be the same for the other. So these, you just have to remember, e to the negative 2. We've got to move the decimal place 2 places over. So this one's 0.04. Yeah, 0.04. This one, 0.01. Are these significant p-values? Yeah, they're less than 0.05, so we know A versus B is not different. I'm sorry, A versus B is different. The means of those are different. These, negative 12, without a doubt, they're different. A versus C is different. A versus D, that's a p-value of 1. This one is 0.17. Is there a difference in A and D? No, no difference. Negative 9, guaranteed difference. Negative 3, difference. Negative 4 is a difference. So really, we're looking at these values, the negative 1s, and possibly the negative 2 that reveal the difference. So how do we go about starting to make sense of this? Well, it's always good to look at our means. So we are doing diameter as a function of site. Data that we're going to use is Oaks, and the function is mean. So if we put these in order from smallest to largest, we've got C is smallest, D, A, and B. So from smallest mean to largest, and I'm doing it up here so I can see my p-values. All right. So we got C, D, A, and B. So just like what we did before, I'm going to look at C versus D first. Is there a difference? Yes. So I'm going to add a line. I'm going to need extra space. A line over C that's separate from D. So I've got my break. Now I go D to A. So A and D is there. There's no difference from D to A. What about from D to B? So that's this one is our fifth one. So there is a difference. So I'll have a break. And now we have to have A to D. A to B. A to B is different. So I get my line. So what it looks like we have is 3 groups. The smallest site, the site with the smallest diameters is C, the site with the largest diameter is B, and the 2 sites with medium diameters that are not different from each other are sites A and D. So let's do our write-up. So with our write-up, get this down here, move it up. We're going to start right from the beginning. So we investigated the diameters oaks at 4 different sites. At 4 sites. So quantile plots. Gosh. Demonstrated normality of diameters at each site, but a Brown 4-site test revealed unequal variances. Alright, so now I have to get my stats. So this is where it works. This helps to actually write stuff out as you go through the assessment. Scrolling up, scrolling up, scrolling up. There it is. Pairwise Welch is ANOVA. There it is. Copy this. Move it down. Paste it. So now we'll use Welch's ANOVA. Suggest that mean diameter varies between the sites. All right, and now I have to go back up and get my ANOVA write-up, which we had just seen it. Copy it, paste it. All right. So now we're on our post hoc test. Pairwise Welch's t-test suggests t-test plural. Site C has the smallest diameter. All right, I'm going to put parentheses where we're going to fill this in. Site D, site B has the largest diameter. Say trees. Diameter trees. And sites A and D have similar diameters. All right, so I intentionally put the parentheses up here and left them blank because we need to discuss how we report these tests now. So with the 2 keys, we did 2 keys, HSD, and we reported the p-value. All right, we didn't worry about test statistic that 2 keys has. We're not going to worry about test statistic here. All right, even though we ran a Welch's t-test, and we would typically report test statistic, degrees of freedom, p-value, and all that stuff, since it forms part of a post hoc test, we are only going to report our p-values. All right, but we're not going to say p equals some value or p is less than some value. We're actually going to say that a p-adjusted value is less than or equal to some value. So this first one, C, the closest p-value that we have is the C to D comparison, and it's this one. It's the -4. So that would be 0.0007 for Bonferroni. So what we'll use is Bonferroni adjustment and specify that p-adjusted, the adjusted p-value is less than 0.0007. But we didn't specify what adjustment we used yet because we hadn't decided if we're going to use Bonferroni or Holm. So here, pairwise Welch's t-test with Bonferroni p-value adjustment suggest. So I wish I could highlight that, but we have to specify what adjustment method we use because that tells the reader how we adjusted our p-values. So we're going to use the top line, or I'm going to use the top line here, and report the p-value. So this is p-adjust less than 0.007 for each comparison because C was the smallest, which meant we compared C to D, C to A, and C to B. We actually did 3. The smallest, or the largest p-value that we had was this, and we report our largest. Site B has the largest diameter trees. Again, we want to report it as a p-adjusted value. We go to B to A, since that's the closest, that should be the largest, and that largest is here. We're using Bonferroni, so we're going to use this value, just 0.04. So p-adjusted less than 0.04 for each comparison. And then sites A and D have similar diameters. And now I only need to go to that one comparison, which is here, and it was 1. So P adjust equals 1. Now, this is a case where giving a p-value of 1 is sufficient because we did Bonferroni adjustment. And what Bonferroni adjustment is going to do is basically take the highest p-value that you get and put that one as 1. Home kind of does the reverse. Takes the lowest p-value, and that's your starting point. So what you'll probably notice is our smallest value. Actually, it takes the largest p-value. That's largest p-value, 0.1729. That was our p-value. That appears in our home. But that does not appear in Bonferroni because that's scaled to 1, or that's moved, adjusted to 1. So we didn't list every test statistic. We didn't list every degrees of freedom. But we're letting the reader know that we did Pairwise Welch's t-test, and we adjusted p-values using Bonferroni adjustment. And if that wasn't enough, we used ADJ as a subscript to emphasize that these are adjusted p-values. Just kind of, again, just reinforce the fact that we adjusted our p-values to correct for this inflated type 1 error. All right? What if we use home? We use home, we just change that. We use with home p-value adjustment, and then we report our p-values from the home line and from this. And again, is one better than the other? Depends if you want to be conservative or be a little bit more powerful. I've tended to lean more towards home, but if you want to use Bonferroni, that's fine.
So for Bonferroni, if you take the largest p-value and it's still not significant, will that convert it to 1 even if it's not significant?
Usually not. Nope. No, yeah, so that's it. That's a good point. If it's not significant, if all of our, and you can see this, if all of our p-values are 2.26 e to the negative 16, the smallest p-value that R will report, that won't like scale them all the way up to 1. It's based on how many comparisons we made. So this up here. This is it. So take your significance value and you divide it by the number of tests, and that's like basically your new significance value. So if we ran 5 tests, 0.01 is your new level of significance. All your p-values have to be less than 0.01 to be significant. You could do it by hand, like what this is, or there's calculators and whatnot. And then you would give in the methods that you're going to use Bonferroni and your critical value or your p-value threshold is 0.01 or 0.025 or whatever. But R does it for us, so that way we just use p.adjust. So this is a great way, and actually we learn this applies for any other pairwise test that we want to run. So if we switch to Kruskal-Wallis test, which is testing medians, and we wanted to do our post hoc test on that, we could do pairwise Kruskal-Wallis tests, taking subsets, doing all of our Kruskal-Wallis tests on each of those pairwise comparisons, and then adjusting p-values. Randomization tests. We do a randomized ANOVA, we get a difference, we can run pairwise randomized t-tests or pairwise randomized ANOVAs, get our p-values, and then do our adjustments. But there's an even simpler function when we only violate our variance assumption, and that is to utilize pairwise.t.test. And you could be wondering, hold on, you could say, hey, this is a built-in function. Why didn't I just introduce this? It's because we have to learn how to do subsetting to do the other pairwise tests. So what is it? Let's take a look at it. Why am I typing? Whoops. Move this over. All right, pairwise t-test. This will do pairwise comparisons between groups. All right, so this will automatically figure out what your groups are and do each of the t-tests for us and report basically a matrix or an array of p-values. All right, we give it our measurement variable, we specify our grouping variable, and then we can tell it what p-value adjust method to use. So Bonferroni or Holm. That works. We have to tell it what type of pooled standard deviation we're going to use. We'll come back to that. We can tell it if we're doing paired t-tests or not. All right. Again, we're not going to use that. That's when we violate our independence. And then we can specify alternative, our alternative, so two-sided, greater or less. Again, we don't do this. If we're using pairwise.t.test as a post hoc test, the only thing we're going to specify is response vector, so our measurement variable, our grouping variable, our p-adjust method, and then this part. So the pool.standard deviation, and that's in our details. It explains what it's going to do. This will calculate a common standard deviation for all groups and uses that for all comparisons. All right? That's if we want it to be true. Or we can specify as false, which will calculate our standard deviation and variance for each group individually. So in one method, if we set pool.sc equals t, it's going to go ahead and run like a regular t-test. It assumes that the variances are equal. If we specify this as false, then we say don't assume that it's equal. Go through and manually do this, which then converts it to a Welch's t-test. All right? So let's see what we can get. So pairwise.t.test. This will run. Actually, we'll come back to this. Let's just get this in here. So pairwise.t.test. We're going to run diameter, but we have to use our data $ variable format, which is, I think, a little less convenient. P.adjust.method. We'll use Bonferroni again, since that's what I use, and we can check our numbers, or we can use Holm. And then pool.sd, I'm going to specify that as false. see what we get. And what I will let you to do is compare these numbers, these p-values, to the p-values that we calculated after our Bonferroni adjustment. Oh no,
I don't know how to make it.
P dot adjust. Better?
Yeah.
All right, so I want you to compare. What we'll do is we'll come back this afternoon. We are. What do we have to do? We've got Kruskal-Wallis test. We'll see. Maybe we'll take a break on. Well, I don't know. Kruskal-Wallis isn't too tough. All right, we're gonna call this quits. We'll be back at 2. We'll record. All right. And yeah, at 2, we'll get the rest of this kind of typed out. I want to get this to make sure you can see the p-values, and then we'll spell out how we do it. All right. See you at 2.
I had an error.